This section introduces Production Activity Control PAC, the function that ensures daily production activities run according to plan. In Chapter 6.1, we look at what PAC is, why it is important, and how it helps coordinate materials, machines, and manpower to keep production flowing smoothly. PAC connects the production plan with real-time shop floor execution. Production Activity Control, or PAC, is all about managing and controlling day-to-day production on the shop floor. It ensures that whatever is planned in MRP/CRP actually gets executed on time. PAC converts planned orders into real work orders, assigns resources, tracks progress, and gives feedback on performance. In simple terms, PAC makes sure production runs smoothly and according to schedule. This slide covers the key objectives of Production Activity Control. PAC ensures production happens as planned, resources are used efficiently, and every work order is monitored closely. It helps detect delays early so corrections can be made quickly. For example, a PAC system tracks multiple work orders daily and reallocates resources whenever a job is running late to protect delivery timelines. This slide shows how PAC fits into the overall planning hierarchy. Long-term planning uses S&OP for balancing demand and capacity over 1 to 3 years. Mid-term planning relies on MPS and MRP to plan products over months. PAC operates in the short-term daily or weekly, focusing on execution and control. The case study from Ford shows the impact. By integrating PAC into their MES system, they achieved real-time visibility into machine utilization and order status, resulting in a 10% improvement in on-time completion. Dispatching is the step where job orders, materials, and instructions are released to the shop floor so work can begin. It ensures smooth workflow and helps prioritize which jobs should be done first. The main functions include issuing work orders, releasing materials, assigning operators and machines, and communicating key instructions such as drawings and due dates. Dispatching is the step where job orders, materials, and instructions are officially released to the shop floor so production can begin. It ensures work flows smoothly and helps decide which jobs should be done first. The key functions include issuing work orders, releasing materials, assigning operators and machines, and clearly communicating instructions, drawings, and due dates. This slide explains the most common dispatching rules used to prioritize jobs on the shop floor. FCFS is the simplest rule processing work in the order it arrives. EDD focuses on meeting delivery dates. SPT reduces overall flow time by completing shorter jobs first, while LPT helps maximize machine utilization by running longer jobs first. The critical ratio rule is more dynamic. It compares time left until the due date with the processing time remaining. A CR value below 1 means the job is behind schedule, while a value above 1 means it is ahead. This slide highlights how dispatching rules work in real situations. In the example, when several orders have different due dates, using the earliest due date rule helps ensure urgent orders are completed on time, even if overall flow time increases slightly. In the Boeing case study, PAC uses the critical ratio rule to dynamically prioritize assembly tasks. This ensures that key aircraft milestones are never delayed, maintaining strict production timelines. This slide introduces key scheduling concepts used in work centers. Scheduling determines when each job should start and finish. Forward scheduling begins as early as possible, helping identify completion dates. Backward scheduling works from the due date backward to ensure deadlines are met. Finite scheduling considers real resource limits, while infinite scheduling assumes unlimited capacity and is more theoretical. Sequencing focuses on deciding the order in which jobs should be processed at a work center. Common tools include Gantt charts for visual timelines, priority rules like SPT, LPT, and CR, and Johnson's rule for two-machine scheduling to minimize total completion time. In the example shown, Johnson's rule helps determine whether job A or job B should go first so that machine idle time is minimized. This slide covers the key performance metrics used to evaluate scheduling effectiveness. MaxSpan shows the total time needed to finish all jobs. Flow time tells us how long each job stays in the system. Lateness or tardiness measures how far a job is from its due date, and throughput reflects how many jobs get completed per unit time. The Hero Motocorp case highlights how digital scheduling helps them resequence assembly lines even during material shortages, maintaining an impressive 98% on-time delivery. Monitoring progress helps ensure production follows the plan and allows early detection of delays or deviations. Common tools include work order tracking systems, barcode or RFID scans, MES dashboards, and daily production review meetings. For example, if a PAC dashboard shows line 3 is producing 20% below target, the supervisor can immediately investigate, such as checking tooling wear and take corrective action like scheduling preventive maintenance. This slide covers the key types of data collected directly from the shop floor. Typical inputs include start and finish times, machine downtime, labor hours and efficiency, and scrap or rework quantities. This data helps PAC understand actual performance versus plan. The whole case shows how electronic feedback terminals allowed real-time capture of downtime and output, enabling daily performance dashboards and faster decision-making at the plant level. This slide explains the PAC feedback cycle. PAC works in a loop. We plan, execute, monitor, take feedback, and then improve future plans. This feedback directly influences MRP, CRP, and scheduling accuracy. Examples include adjusting MRP when delays happen due to material shortages, correcting routing when rework times exceed standards, or modifying CRP when capacity is underutilized. This slide highlights the key KP is used to measure PAC performance. Order lead time tracks how long jobs take from release to completion. On-time delivery measures reliability, rework and scrap percentages show process quality. Labor and machine utilization reflect how effectively resources are used, while schedule adherence compares actual progress with the plan. In the ABB India case, standardizing these KP is across plans improved visibility and root cause analysis, helping them reduce lead times by 20%. This slide highlights key visual controls and communication methods used on the shop floor. And boards give instant visibility of production status. Daily huddles improve communication between shifts, and visual scheduling boards like Kanban help teams see work progress easily. Real-time alerts ensure quick escalation whenever issues occur, keeping production on track. This slide compares infinite and finite scheduling. Infinite scheduling assumes unlimited capacity, making it fast but less accurate and often leading to overload. Finite scheduling, on the other hand, considers real capacity limits, making it more accurate and practical for shop floor execution, though it is computationally heavier. Infinite scheduling suits high-level planning, while finite scheduling is used for detailed execution. This example shows how finite scheduling prevents overload. When an MRP run creates more orders than the press shop can handle, finite scheduling automatically shifts extra work to the next available time slot. The Toyota case highlights this. In practice, Toyota uses finite scheduling integrated with Kanban, ensuring no job enters production unless capacity actually exists. This keeps flow smooth and avoids bottlenecks. A bottleneck is the resource that limits overall throughput, and you can spot it through symptoms like queues, delays, and VIP buildup. Common detection methods include throughput rate analysis, utilization reports, and direct Gemba observations. Identifying the bottleneck is the first step toward improving flow. This slide explains the 5 steps of the theory of constraints. First, identify the constraint. Next, exploit it by using it fully with no downtime. Then subordinate all other processes to support the constraint. If needed, elevate it by adding capacity. Finally, repeat the cycle for continuous improvement. The example shows that if a paint booth can only produce 40 units while upstream can make 60, all scheduling must revolve around that bottleneck. Buffer management ensures smooth production by placing time or inventory buffers before the bottleneck so the constraint is never starved. This keeps the flow stable and maximizes throughput. The GE Aviation case shows how applying torque on their engine assembly line helped reduce lead time by 28% and increased throughput without needing extra capital investment. This slide explains the key KP is used to measure capacity performance. Utilization shows how much of the designed capacity is being used, while efficiency measures how effectively available capacity is converted into output. OE combines availability, performance, and quality to give a complete view of equipment effectiveness. Throughput tracks how many units are produced per hour and reflects flow rate across the system. This slide highlights ways to continuously improve capacity. Techniques like SMED reduce setup time, preventive maintenance increases availability, and cross-training boosts flexibility. Data-driven monitoring through IoT dashboards helps identify capacity losses early. The Tata Motors case shows how OE monitoring encases an improved line efficiency from 78% to 88%, adding 10% extra capacity without new investment.